But he owned up to it, like, you know. And I was like,
All right. So how's everyone doing?
that's so bad.
All right. At this point, we have concluded chapter 9. We've gone over all the pressure and buoyancy stuff that you guys are going to need for the course, and so that means that we've covered the last pieces of information of learning done up to the test. My main goal for today is to go over absolutely everything that you guys will need to know before the test next week. And again, as a reminder, test 2 is next week, but again, it's during lab like the last one, so lecture will still be practice and review time for next week. The report to take the test when you would take lab, that doesn't mean there is a lab, it means you're doing this instead of lab. Getting a little ahead of myself. We'll go over everything you need to know before the test next week. Before that though, any questions from you guys, possibly about chapter 9 or any homework you've been working on? Yes?
So number 1 of the chapter 9 quiz, I don't.
All right, let's take a look.
Is when I use the formula, I don't get it right.
This one, right? All right, we've got a balloon filled with helium, mass, and the radius of the balloons, estimate the total buoyant force on that many balloons. Okay, so helium balloons float because they are filled with helium, which is less dense than air. This wasn't actually what we need here is the density of air, which this does not give us frustratingly. Didn't quite realize that at the time. So what I'm going to do is I'm going to work this one all the way through with the density of air that I just looked up to make sure that it works. So density of surface level air, at least 1.225 kilograms per meter cubed. Excuse me. So each of these balloons mass of such and such. Oops. Again, my red numbers are going to be randomized, so that'll be the part that you'll have to change on your own. Radius of each balloon is 0.51. That was already meters. Very good. Achieve the record altitude by 600 balloons. If we're using buoyant force, then okay. So my first thought is total buoyant force on the 600 balloons. We're going to first figure out the buoyant force on a single balloon and multiply it by 600. Buoyant force is density of the fluid you are submerged in times the volume of the object times gravity. So for a helium balloon floating in air, the fluid it is submerged in is normal atmospheric air. The helium inside is just less dense than that. So density here would actually be that of air. That's why I had to put that one up over there. I'll work it through to make sure that number works right. Volume of the object, that would be the volume of, I guess, 600 balloons. But first I'm just going to find the volume of one balloon. Because the question only gives you radius, you're going to have to find the volume of a sphere based on that. Which I will also put on board so that you can copy that down. Volume sphere, 4/3 pi r cubed. So whatever radius your balloons were, based on the slight randomization of numbers here, volume 4/3 pi times whatever your particular radius was, cubed. It's already in meters, so you don't need to convert anything. So my volume turns out to be, for a single balloon, volume, single balloon is about 0.556. If we then try to find the buoyant force on a single balloon, there should be about 6.67 newtons of upward force on that balloon. And just to check, if I multiply that by 600, okay, I get 4,002 newtons. That is not what WebAssign was expecting for the answer. Did you do something like that?
Yeah, I did.
All right, so I wanted to work it out. Apparently, there's something wrong with the code here. I'm assuming it might be using a different density for air. So we need to figure out what that density is. It's expecting 4,215 divided by 600. Buoyant force should be 7. So divide that by the balloon's volume and gravity. It appears as though WebAssign's definition of air density is closer to 1.289. So my first thought is, if you rework it with that, it's still wrong, then it's a bad question, I need to change it.
Yeah, it works with that.
Okay. Apologies for that. Most of the times the questions give you all the densities they needed, but somehow this one didn't, and that slipped through the cracks when I was assigning everything, so I apologize for that. So, official announcement. Chapter 9 quiz, question 1. You'll need these pieces of information. As for B, the upward force on the balloons should be the answer to part A minus their weight. And you have the mass of the balloon. So find the weight of one balloon, multiply that by 600, and then subtract that from the buoyant force upwards. And then balloons start popping at high altitude because the pressure at high altitude is lower than on Earth's surface. Answer to C should be the same for everybody, so you are allowed to look at that. Actually, to elaborate on why that happens, tend to be inflated on Earth's surface, because that's where we live and where they are manufactured. And so if you inflate the balloon down here, the pressure inside the balloon should actually be the same as the air pressure outside, because it was inflated down here and the pressure's equalized based on that. But as the balloon physically elevates, the air pressure up there is a lot smaller, right? We already talked about how the higher up you go, the less air is above you, therefore the less pressure that air generates. So the pressure inside the balloon doesn't change, which you might know from chemistry work. As long as the amount of gas inside stays the same and its temperature stays the same, then the pressure of the gas inside should stay the same, but the pressure in from the outside doesn't. So as the outside pressure weakens, the balloon actually starts expanding until it just pops. Does that address the concerns of this question? All right. Anything else on your minds here at the start, namely about the homework or quizzes? In that case, let's turn our attention to next week. As a reminder, today is the 10th. Wait, what holiday is that? Why is the 10th red?
Veterans Day.
Oh, wow.
Yeah.
How did I not notice that? Anyway, next week, the 13th to the 17th is when the test will be given. Again, that'll be during lab. You can take it during any lab time that week, except, again, Thursday. Thursday is a May. But test will be done by that week. All lectures that week will be focused primarily at review. You come in, we group study sessions, basically. So if you don't need those, or if you take the test and complete it, officially, one would not need to come to class anymore that week unless you absolutely want to. So, if you take the test Monday and then you're done, it's early Thanksgiving. Well, not quite, because the week after that's Thanksgiving break. We are going to meet Monday, because my plan is to have the test graded and handed back that day. So you will know before break how you did, and then you just don't have to worry about it. Then Thanksgiving break. We meet again the week after that for one more chapter, and then exam review. Calendar look good for now? Yes.
How much is test 2 worth?
Tests as a whole make up 38% of your grade. So which means each test is functionally about 19% of your grade. So again, hypothetically, if you just bombed test 2, didn't write your name on it, didn't write anything down, handed it in blank and got a 0, 100 minus 19, you could still get an 81 in the class. And again, the only way to get a 0 on my test is literally to leave it blank. Does that answer the question?
Yes.
And then after that week, we'll be on the last chapter, and then we'll take our final.
Yes. November 27th through Friday the 1st is the last full week of class. That week, we got one more chapter I want to talk about, and just to let you guys know, it'll be about sound and waves, and then specifically sound waves. Then Monday, December 4th, we do still have normal class that day, but by that point, we'd be wrapping everything up, doing exam review. And then Tuesday's reading day. Is Tuesday reading day? I think Wednesday's reading day, but I just don't see you Tuesdays. And then Thursday the 7th starts exam season. And this class's exams are either Thursday or Friday, just depending on which of those 3 day times you'd like to come to. Officially, this section's exam is Thursday at 5:30, but if you'd rather one of the others, you may. Okay, I'm giving the same exam all 3 times. I'm gonna be here anyway. I don't care when you show up, as long as it's one of those 3 times. Does that answer your question? Okay. I feel like when I start talking, I get sidetracked, so I have to check. Where did I set down my water? No, I never removed it from the bag. All right. So. No, that's not what I meant to go. There we go. I have updated the test 2 information on Brightspace. Test 2 will be on chapters 6 through 9. The information from those chapters is outlined here. I want to step through this list and make sure that I have told you in absolute terms what types of questions you should expect. First up on this list is actually kinetic energy, which was technically chapter 5, but we utilized kinetic energy all the way through chapter 6, 7, and 8. So you do still have to use linear kinetic energy, and as a result, velocity and mass as well. But you need linear kinetic energy because we specifically started using that in momentum questions. Momentum, starting from chapter 6, that was, again, how difficult it is to stop a moving object. And we primarily looked at momentum through the lens of collision type questions. So you do have to be able to do collisions. Those questions, again, they involve one object physically colliding with another. The collision is either going to be elastic or inelastic, and they typically start like this, where you're comparing total momentum initial to total momentum final. So there will be momentum collision questions. You do have to be familiar with the difference between elastic and inelastic collisions. What is that difference? In elastic collisions, the objects tend to stick together, whereas in elastic collisions, what happens instead?
They bounce off each other.
Bounce off from each other. Now, what do those 2 differences imply about the kinetic energy between the 2 types?
Inelastic, only the momentum is conserved.
Correct. And then in elastic,
Kinetic energy.
correct. Momentum is always conserved. Collision type only affects whether or not kinetic energy is conserved. So, looking at collision type questions, it will always tell you if it's elastic or inelastic, but based on that assertion, you then have to choose what assumptions you can make about momentum and kinetic energy in that example and what sorts of starting points you can use for it. This is good for any collision, because momentum is always conserved regardless of type. What your formula sheet will point out is that kinetic energy, total kinetic energy, is only conserved for elastic ones, and there's another formula on there that also works only for elastic collisions. Your formula sheet pairs these 2 up together. They both only work for elastic. You cannot use this for inelastic. Yes?
If we're doing elastic and we have to do like a 2 equations for unknowns, is that what we're practically always going to use for that?
Yes, if you had to do in elastic 2 equations, 2 unknowns, you'd have to pick 2 of these, and I'd recommend the first one and the third one just because there's fewer things to deal with. If you need practice for that, I have included a practice question about that in the practice test, which is updated, and I'll post the answer key for it today. So, the chapter 6 stuff right here, momentum, be familiar with the concept itself, be able to apply it to conservation of momentum in a collision. compare that to conservation of kinetic energy when it is conserved, and also remember the definition of impulse, which is just change in momentum.
Since we're on that topic, can you go over number 7 on the chapter 6 homework?
Question 7, chapter 6. Ah, yes. So this is an elastic collision, and it is also utilizing some concepts from chapter 5. These two objects are starting at either side of this skateboard ramp, basically. And the two objects start in an elevated position. So what form of energy do they have up there?
Potential.
What type of potential?
Gravitational.
Gravitational. They are elevated, there's no spring or elastic object, they're just beginning some height above where they're going to end up. So both masses start with GPE, and what does that GPE turn into as they slide down? Kinetic energy. So, part A of this question, before the collision actually starts. So part A isn't really a collision yet. Part A is noting that there's going to be an energy transformation and comparing the initial GPE to the final KE and using that to determine the velocity of each object. You know, the speed they're going to be moving at once they reach the bottom of a frictionless ramp. Even if you're not falling, GPE still turns into KE as you descend. So that's what's going to determine their speed before impact. And part B is then looking at what will happen during the impact. And part B is specifically collision between an elastic collision between the two objects. So as pointed out earlier, since you don't know the final velocity of either object, if you say look at conservation of momentum, you know their initial momentums because you know their mass and initial speed, but you don't know either their final speeds. So there's two unknowns there, and you'd have to use a second equation with the same two unknowns to consult and combine together. That is a problem that just tends to happen in an elastic collision if you don't know either final speed. So part B is the part that will take the most algebra here. Main things I'd point out are you have to pick two of these three. This one and this one are the easiest because there's just a square in the kinetic energy one and it's a headache to deal with. And you should set the expectation that one of these masses is going to be knocked backwards. Originally, one of their speeds has to be negative because they are both moving in opposite directions. Same is true after impact as well. They just kind of they turn around, and so the positive one becomes negative, the negative one becomes positive. So set the expectation of one of the answers being negative. And then part C is kind of the opposite of part A. After the collision, they're gonna go back with their new velocities, and that's gonna determine what height they slide back up to. So part C is the reverse of part A. Does that address your concerns?
Yeah, thank you. I just I was doing the problem and I was able to get part A, but then I wasn't able to get part B, so I guess I was just using the
B is the part with the most algebra. Like there's the most steps, there's the most places where, you know, anything can go wrong. The more things you have to write, the more anything can happen. If you'd like, I can check over your work specifically later, if you just want to show me your scratch work.
I erased it.
Oops. No, well, we can redo it on the board later if you like.
Okay, thank you.
Welcome. But it's a very good example of the type of collisions things that you're gonna have to be able to know for the test. And again, there is also practice for that on the practice test. That was all the chapter 6 stuff. Chapter 7, and by extension 8, begin our study of rotation. So here we've got rotational motion, angular displacement, velocity, and acceleration. For that, you should be familiar with all of these angular versions of the old linear formulas. Understand that they work like the old ones, but you're working in radians instead of meters and spinning instead of moving forwards. But you should be able to, say for a spinning wheel with a radius, convert back and forth between the two using those intermediary statements there. Understand how the wheel's rotation is still tied to the speed that it is moving forward at, and be able to examine the motion of spinning objects. Sometimes they spin and don't move forwards, but if they're doing both, you need to be able to convert between the two. Chapter 6 also contained centripetal force and centripetal acceleration. This is the force that causes one object to spin around something else outside of itself. The word for that is orbit. So be able to calculate centripetal force acting on a spinning object. And you also need to note that centripetal force is not centrifugal force. This only comes up as a vocab word because centrifugal force, again, is not a real force. There's no force there to calculate. It's just a perception because of quirks in the human body. You do feel something, but it's not technically a force, and that's why we call it a fictional force. There's something there, it's just not a force. And you need to remember, centripetal force is the real one that we calculate. Centrifugal force is the sensory perception that is not technically a force. The way that I always would remember it is just that centrifugal has an F in it for fake, or fictional. Again, centrifugal force is just a vocab word, but say how there was a laws of motion question last time. I'm not very unsubtly pointing out that there will be a part on the test where you might have to explain to me the difference between centripetal and centrifugal. And again, the answer is centrifugal force isn't real. Now, what you're going to have to do with centripetal force is, one of the things we did most often with it was compare it to the universal law of gravitation. That was, again, the definition, the explanation of how gravity works in the universe as a whole and not just on planet Earth. The formula that lets you calculate the gravitational pull between any two things, as long as they have mass and a distance apart. The main place we used that law was in conjunction with centripetal force to calculate orbit. So just as to review slightly, we got moon. Moon has velocity forwards. Moon's being pulled down by Earth's gravity. Those two things at the same time cause a circular motion around the planet. And the way that we can calculate that is by physically setting Earth's gravity equal to centripetal force, because Earth's gravity is acting as a centripetal force. So for an orbit type question, moon around Earth, satellite around Earth, random piece of space debris around Earth, anything like that, this is your starting point. This is the way that you would solve an orbit type question, like there may be on the test. Strong suggestion. And from this starting point, you would again replace Fg with the universal law of gravitation formula and Fc with the centripetal force formula. So big G m1 m2 over r squared is equal to either m v squared over r or m omega squared times r. Those are both valid versions of the centripetal force equation. It's just a function of, do you know v or want v, or do you know or want omega instead? So you just pick the one that's most relevant to the question at hand. Sound familiar? All right. A couple tidbits I want to make sure are set in your notes and in your brain. It's the same r in all of these, it's always the radius between the centers of the two objects, since that's both the orbital radius and also the distance between their gravitational centers. So it's the same r throughout all of this. And again, that's always distance from center to center, not surface to surface. And this m, in either version of the centripetal force equation, is gonna be the same as one of these two m's. It's always, this one is always the mass that is doing the orbiting, not the mass that is being orbited. So this side, if you were doing moon and earth, moon's mass would go here, whereas both masses go here. So the orbiting object goes over here, both go over here. And in a weird way, that kind of ends up canceling the mass of the orbiting object. But you need to note which one goes on which side, because you want the right one to cancel. So, universal law of gravitation, combination with centripetal force for orbit. Sound good? Alright, that was chapter 7. Chapter 8 was a direct continuation, looking at more rotational concepts. Main ones I'll point out are moment of inertia, since any linear concept that has mass, you need to use moment of inertia in the angular counterpart instead. For that, what you're gonna need to be able to do is, if I tell you that an object is rotating, and I tell you what type of object it is, namely what shape it is. So say I tell you a cylinder is rolling along the ground. That's your cue to look on this page of your formula sheet and find the moment of inertia formula for cylinder. Whatever shape I tell you, you consult this, you use the moment of inertia formula for that shape. And then you physically place that into the other formulas that have capital I in them for moment of inertia. The formulas that use the moment of inertia in them are torque, rotational kinetic energy, and angular momentum. Since they're linear counterparts, I'll use mass instead. Torque's the counterpart to force. It causes things to rotate instead of move in straight lines. Rotational kinetic energy is the counterpart to linear kinetic energy, and the angular momentum is that of linear momentums. They all work like their old counterparts, but yeah, just spinning instead. I'll give special attention to torque real quick though, because we spent a few days looking at, level balance beam torque questions. So you do have to be able to use torque, net torque of 0, to equalize a seesaw, like in lab. In fact, lab is great practice. You should look over how lab went. To that end, there is also a seesaw question with practice test. Sorry, distracted myself real quick. Then, that was the end of chapter 8, and this last blurbs here was all the stuff we covered in chapter 9 this week. Density, just for use in other formulas. Pressure, defined as force exerted over surface area. How to calculate pressure at a depth within a fluid. And buoyant force, how to calculate the force the fluid exerts up on you if you are submerged in it. Extra thing to remember about buoyant force, something floats if buoyant force equals its weight, assuming that there's no other outside forces acting on it. So that's another thing to remember. There will be a question about something floating. If it is floating unassisted, weight equals buoyant force. And that is a quick summary of all the types of information and types of questions you'll have to do on the test. questions, feelings, opinions? Alright. The test draft is finalized, and as such, I have based the practice test around it. As a reminder, there's now a practice test, an updated practice test posted on Brightspace. There was one there from last year, bless you. It has now been updated for this year's specific version of the course. Again, this is always the practice test. Always has more questions on it and is usually more difficult than the test itself because I'd rather you make mistakes here than there. So keep that in mind. Yes.
For the chapter 6 one, like, there was one where it was like a ball bounces against the wall and it showed like the angles. Are we gonna do that, or should we like practice that?
No. And for that question, wait, hold on. I wanna look at it real quick to make sure I'm remembering it right. This one?
Yeah.
All right. Along the same street angle. Oh. Yeah, this is just basically impulse with extra steps. By that I mean the wall can only exert force this way, meaning that you need to figure out how fast the ball's horizontal velocity is, because the wall can't do anything about the vertical velocity. So this is just the definition of impulse with extra steps. And I will go ahead and say, for full information's sake, when I say extra steps, I mean dealing with the angle here. That's not on the test. Did I address the concern? To kind of mention what will be on the test again, looking at the practice test, you do have to tell me the difference between centripetal and centrifugal. The difference is one's real, one's fake. You have to remember which is which. Again, you also need to definitely know the difference between elastic and inelastic. Momentum is conserved in both. Kinetic energy is only conserved in one. You have to remember which is which. This, number 5, is an orbit question. We've got a meteor orbiting the Earth. Again, you would treat that like this. Rotation, namely converting between linear and rotational. This is collision impulse, rotational kinetic energy and momentum. This is the balance beam question on the practice test. Note that it's not literally a balance beam, but it still uses the same concepts. So if you can do a level balance beam, you can do this and then in turn apply this back to the linear balance beam. I'd say the main trick with this one, like the one we did in class, is one, the hinge is here, meaning everything is to one side of it, and what direction the torque it generates depends on the direction of the force. So upward forces would make counterclockwise, downward forces will make clockwise. And the other, again, this is more difficult than the real test. The added difficulty for the practice test is this angle here. Remember, the rule for torque is the force only creates torque if it is perpendicular to the radius. So however much force is needed vertically at this spot, that's only going to be the vertical component of the tension in this rope. But as long as you can find that vertical component, that's the main thing. The 45 degrees is just, if the rope is tilted, how much more torque tension does the rope need because it's tilted? If you can do a balance beam, you can do that one. If you can do that one, you can definitely do the Berkeley Allen test. Anything else on here I want to mention? 10 is a collision question, and I give basic premise about the two objects colliding, and then I'm going to show when I post the answer key my work for the inelastic version, and also separately, the elastic version. Like using the same question the two different ways to demonstrate the difference between the two and demonstrate how radically different the two outcomes are. So on my answer key, I'm gonna show both versions, and you wanna make sure that you understand the differences between the two types. And last couple pages are the pressure and buoyancy stuff we've been doing this week. So, I guess Phil. Anything else on your minds before we call it for the weekend? All right. And that's pretty much it for today. So weekend and also lectures next week will be study stuff. So any issues and questions at all you encounter while studying, please email me. And also, you can bring them to lecture next week. We can work on them together. We can practice test homework, nothing's off the table. I'll say again as a comfort, you can choose what day you take the test. If you just don't feel up to it Monday and or your schedule allows for it, you can switch around days of the week. Also, keep in mind I write the test so that it takes most people an hour to do it. I'm not writing this to take an eternity. That's my test philosophy. I'm not trying to create something super difficult here. I'm writing questions that I know you can do. I believe in all. Again, this is more difficult than the actual abstract. I promise you that. Have a great day. Have a great week.